Well, thank you everyone for sticking around to the last talk. I'll try to keep things relatively short, and we can all get on our way to whatever was coming after this. So yeah, I'm going to talk about the Unitary Compiler Collection, which is a technically yet to be released project. So this is a bit of a sneak preview. The GitHub is public, but we haven't officially kind of put it out there. So this is kind of the first getting a first preview. So this is the team that's been working on it. This is our fun logo. There's a sticker over here for it if you want to take one. Jordan has been leading this project. So unfortunately, they could not be here, but yeah, this is props to the team. So let's go over what's in the name. So Unitary Compiler Collection. So unitary because unitary matrices and unitary operators are the things that underlie quantum mechanics, the things that we operate on in quantum computation. And then compiler. Compilers are things that translate code from usually a higher level of abstraction to a lower level of abstraction. And just a note here on terminology. In quantum, the word transpiler is often used, or maybe a gate optimizer or something. And usually these things are used when the level of abstraction is roughly equivalent. So if you're taking a circuit and optimizing it, and we'll go over an example of that. And then a collection, a group of things. The idea here is that we don't want to necessarily be the only ones developing things like transpiler passes because there's only so much that a limited group of people can do, and also every application of quantum computation may need a different particular compiler pass to make the problem more efficient. And obviously, what's in the name is reminiscent of GCC, the GNU Compiler Collection, and taking a lot of inspiration from the classical compiler infrastructure that's been built over the past 50 years. And there's already a lot of things happening in that area, but yeah, obviously want to take away a lot of lessons from things learned in that development. So first, let's just talk about what is a quantum compiler, or maybe in this instance, this is going to be something we're going to do a transpilation and then a compilation as well. So we've seen a bunch of quantum circuits already in today's talks. And so we're going to think about what are some operations that we can do on a circuit that looks like this to reduce the gate count, reduce the depth of the circuit, and ultimately when we run on a quantum computer, we want our circuits to be as short as possible because they'll run faster, there'll be less opportunities for errors to occur, and so we get more accurate results. And errors are generally something that happen a lot more on quantum computers than they do on classical computers. When we do classical compilers, we just want to make things fast. And error correction is a thing, but a lot lower rate of errors on a classical computer than a quantum computer. All right, so let's zoom into these two gates. Let's just say, for sake of example, that they're two RZ gates, and they're very similar type of gate, but they have a different angle that's parameterizing them. We can take that, we can compile that into a single gate where the argument or the angle that you're rotating your qubit by is the sum of those two angles that you were doing previously. Okay, that's a very simple one. That's like a peephole optimization. But these are things that you can take into account, and you can, you'd rather do that rotation in one operation rather than do a rotation and then take the next step and then do another rotation. Okay, so now we've compiled. We've made our circuit just a little bit shorter. Now let's look over here at these three operations. Let's say in this example that we have a C0 and then we have two Z gates. So the C0 operation is the controlled NOT, and a little bit of mathematics. You just massage the matrices a little bit will show you that you can actually just do one Z on the target qubit before the C0, and that's equivalent to doing two Z's. Basically, the Z propagates through the C0 in such a way where, instead of doing two Z's, you can do one. One gate reduction. Wonderful. Okay, so we've done that. Those are just, again, some examples of maybe what people would call peephole optimizations. They're just nice little tricks, basically. And now let's say you're ready to take this circuit and you want to go run it on on some QPU, on some quantum hardware. Most quantum hardware does not have a 3-qubit gate. And so whatever classical software that you use to generate this circuit, maybe doesn't know that, and maybe you probably don't want it to know what the hardware actually looks like. You want it to generate something, and then you compile. So then, let's say, for example, a common 3-qubit gate is the controlled not gate. And you want to say, okay, the computer can't do that, so I need to decompose it into operations that the computer can do. Okay, and there is a nice decomposition of the controlled not, or the Toffoli gate, into single qubit gates and 2-qubit gates, but it's really, really big. So it introduces a whole lot of new gates and new operations into your circuit. Okay, so now we're getting this idea that we did this decomposition, and now you might want to redo some of the optimizations that you've had previously, because maybe this Hadamard gate actually can join in this operation, or maybe there was a gate here that it cancels with, and you want to do some analysis after you do decomposition. But let's say you go about doing that. You do another compilation pass. And there's one other thing, which is, let's say you're running on a machine with limited connectivity in the qubits. So right now we're introducing an operation that touches qubit 1 and qubit 3. But what if those 2 qubits on the device are not actually connected in such a way where you can do a 2-qubit operation between them? Then you need to introduce swaps, or you need to rearrange the qubits so that the ones that you're acting on are they actually have some physical coupling on the quantum computer. So now there's no operations between qubit 1 and qubit 3. Everything is just between 1 and 2 and 2 and 3. So we've satisfied what's called the coupling map constraint, which is sometimes referred to as qubit routing, qubit mapping, these kind of things. So you can see all of the problems that we're dealing with, though, are very intertwined in that you may want to do one and then go back and do an optimization pass and then do another and then optimization pass. So it's not very trivial. Okay, so that's our quick example of doing quantum circuit compilation. That's the overall goal that UCC is working towards. And so why are we building a new tool? We've heard a lot about a lot of the existing tools that are out there. So let's take a look at what the ecosystem looks like. And highly incomplete picture. There's 20 more blocks here of companies with their own specific tooling mostly. And Google has Circ, and they transpile down to their QPUs. And IBM has Qiskit, and they have a transpiler or compiler down to their hardware. And basically every company is doing this because the tools that are extremely useful just don't exist for everyone. This creates a problem. Oh, and there is CHASM. We've heard a little bit about that. There is CHASM, which kind of goes to everyone, but not everyone has full buy-in as to using CHASM to be an intermediate representation. And so it's important to look here, what's so good about classical compilers? What have they enabled? And what should we be drawing from them? So there was a question previously about the diagram that Harshit showed previously. It has this network, and in order to compile from one, you take this path on a graph, and someone asked about a hub and spoke model, and that's very much intimately related to, in classical compilers, one thing you can have, or when running classical code, you can have maybe you have whatever language you have, but then you want to run to different backends, and you can support a direct pipe to each one of those instruction set architectures. But this is very intensive, because then you need a connection between every language and every backend, which is, one, a lot of code, and two, it's a lot of maintenance that needs to be kept up. And as something changes on the instruction set architecture, you need to maintain every one of these n times m connections. So, obviously, one thing that's been learned in classical compilers is that if you have a standardized intermediate representation that the compiler can operate on and do most of the optimizations on, then you only need to maintain, like the Rust to LLVM IR pipe, and then all the optimizations can just happen on that, which is a much conceptually simpler and reduces the amount of work and maintenance that needs to go into like this whole infrastructure that we need to build. Okay, so that's the motivation behind UCC. How do I install it? It's a Python package. You pip install it, and then using it. Right now, we support these 4, however you define your circuit, and it's just a call to ucc.compile. We've made it to be very extensible, so if you want to do a custom optimization pass or something, these are the default passes that happen when you run UCC, just names. If you want to define a custom pass, let's say you want to do some fancy Lie algebra decomposition of your unitaries, you basically just make a new class and you inherit from something like a transformation pass. A lot of what we've built so far is basically extensions of Qiskit, because the Qiskit compiler is quite good and quite performant. And we want to plug in other compilers to it to see, like, as we've been doing, to see if we draw from multiple different places, can we get performance gain? So here's just some plots of how it performs. Generally, what you want to be looking at here is like this is compiled gate count, so you want lower. As you can see, the compiler that we've introduced, UCC, is performant with everyone else. And everyone basically does most of the same things, so we still need a lot of compiler research to continue pushing down gate counts. But yeah, we're competitive with everyone else. But this is a very new project. We need lots of new ideas. The compiler infrastructure for Quantum is relatively lacking, as everyone has heard today. Like everyone has their own tooling, and there's not a ton of collaboration between the companies, between the silos of information. So yeah, here's our repo. We have some documentation, but we need people using it. We need people testing it out. And so yeah, if you have a quantum workload, please just check it out. And then just the last thing, a little bit of advertisement for Alessandro and I both work for the Unitary Foundation. If anything that you saw today inspired you to want to work on quantum software, the Unitary Foundation gives microgrants to people who are doing this, no strings attached. It's $4,000, and it's generally for things that are open source, community projects. Whether you're developing HAT, we had given a microgrant to the talk that we saw previously about quantum type language. It's a short application. And yeah, so you can go here, unitary.foundation/grants, and get some more information. And yeah, please check it out. With that, thank you all again for coming for today. Yeah. I forget what the QR code is. I'm pretty sure it's to our repository, but you just get it and find out. Sweet. Well, that's all for Quantum Computing Dev Room for 2025. Yeah, thanks everyone for your participation.
We have a minute of